I'm starting. Actually, I updated the YouTube channel. I think I promised you to do that last time, or maybe not. But anyways, all the lectures up to the last one, including last Wednesday, are on this channel. So this way you don't have to dig through emails. In fact, the last emails, they disappear, right? So this way, I guess you don't get those recordings, but not really, because they're all now on the YouTube channel. So as I said, I will be updating it every few weeks. So next time I'll do this again sometime at the end of November. So this way you'll have a nice set of recordings that you can concentrate on before the final exam. So anyways, the antiderivatives time. So I'm gonna add one. So how do I produce 5/2, first of all? So when I multiply t to the power of 1/2 by t squared, which is 4/2, right? Because when you divide 4 by 2, you get 2. And that's how I get t to the power of 5/2, because we add powers. When we multiply the powers, we add 1/2 and 4/2. So that's how I get 5/2. So now I have to subtract from it 1. So my power now, according to the formula, will be not subtract, add 1 to the power of x. And the same number I need to put in denominator. So what is 5/2 plus 1? Well, 1 is 2/2, right? 2/2. So when I add it, I'll get a 7 of these halves. So that's what I have in denominator of the first one. And then similarly for the second. So I have to add a half with 1, which is 2/2. 1/2 and 1. And when I do this, I get 3/2, but I can actually, instead of 1, again, write it as 2/2. So we end up with 3/2. I hope that eventually you'll start feel more and more comfortable doing this arithmetic. I know if it's been a while, then you may not feel very good about this, but you could use calculator. Calculator will give you decimals, but I guess it's okay. I'm not going to pick on that, because I will be in a good mood when I grade your final exam, right? And plus the constant. So that's one thing that you should not forget. In fact, I know that some instructors might not even give any credit for the exercise if you forget about this plus the constant. Eventually, I'll tell you why this is so important. So far, we just learned the procedures, but then eventually we will see what these constants actually designed for. So anyway, 7/2. So we have to flip this and it'd be 2/7, right? So whenever you divide by fraction, you actually multiply by its reciprocal. And t is still raised to the power of, we already know what it is, 7/2. We just added, right? Analogously with the next one. So we flip that 3/2 and get 2/3. And then t is raised to the power of this 2/3. 3/2, sorry. You can write them as radicals if you want, because if you have the fractions and your powers, they be square roots. But who needs that? If I write it as square roots, I don't think it will be looking much nicer. I can still write it if you want to. It's the same thing. So I'm not asking you to actually do this, because it's not really changing anything here, but just gives you some radicals here, like t cubed. And some people might even pull out some t's, some powers of t from these radicals. But again, it's not really what we're after when we do calculus, because it depends on the nature of exercise that you're trying to solve. Sometimes you don't have to do this. So another little problem, exercise 25, I just saw that attracted me. And it's not because we have this See, part of this erased. Not because the formula is very nice, but because we can't really take it the normal way. In other words, if I integrate e to the power of t plus 1 squared dt, I don't really have a formula for that. The formula that we have is here. That's my favorite formula. Formula for the e to the power, for derivative of e to the power, which is exact same thing. I say, Alex, what's the problem here? Well, the problem is that we don't have e to the power here. In the parentheses is e to the power and plus 1. And that's what is on the way. So this is something that stops me from doing this integration. And what people do for this matter is they use so-called substitution. Turns out people will replace this with a new variable letter u. So now this is a key part of this rest of the class. The process of taking antiderivatives using the so-called substitution. So it says that whatever you have in the parentheses, always call it as new variable letter u. And then you substitute parentheses. Now I need to also replace dt. And the way to replace dt, that's a function u of t, then you take derivatives on both sides, so you get du over dt. That's another way to write derivative. I used to write it as u prime, but now I want to call it as du over dt and take derivative of e to the power, which is the same exact thing. One is constant, it disappears. And then there is one little extra step. I can multiply both sides of this by the same expression with dt. And this way I can cancel that expression and just see what is that we produced in here. And what I produced is something that may not be very nice, because I don't think we'll be able to take now this antiderivative, because this is going to be u squared. And instead of dt, instead of the other piece, I'm going to have du over e squared. Yeah, the substitution didn't work. Anyways, I tried. See, sometimes you start solving these exercises and get to the dead end. And then you start wondering, so how can I possibly solve this exercise? And the answer is, well, you need to square that thing. I tried to get a shortcut and illustrate the next section for you, but I guess it's not the time yet. The time is to actually square. The time is to do same thing as we just did in the previous exercise, to simplify our integrand, because the problem here happened with my so-called little substitution. So what I need is to think of e to the power of t plus 1, since it's squared, well, then multiply it by itself by another e to the power of t plus 1. Because that way you will be able to actually distribute and produce little pieces of the kind of integral that is my favorite. So when I multiply e to the power of t by e to the power of t, I'll get e to the power of 2t. You say, are you sure? Well, e to the power of t times e to another power of t will be e to the power of e to the power of t plus t, right? We add powers. That's the rule of multiplying. And when I add t and t, I get 2 of those t's, just like that. But that's not it. Now I have to continue. I just multiplied first terms. Now I get to multiply the middle piece and the piece on the outside. And notice they're going to be the same. They both e to the power of t, right? Just like when we FOIL. So when I put them together, e to the power of t plus another one, I'm going to get two of these e to the powers of t. And then finally, my favorite, 1 times 1 is 1. And that's what I'm going to try to integrate. So I'm going to have to take 3 integrals. E to the power of 2t. That's where I'm going to show you the substitution. See, I felt that this is a substitution, but I should have simplified first. Next is 2 times e to the power of t. And the last one will be just 1 integral of 1, and that's your favorite. In fact, when you took the quiz, I was impressed because I think pretty much everyone done it correctly. So you definitely know how to integrate this guy. So it'll be just letter t, right? Because derivative of t is 1. Now, what's with the middle one? Well, 2 stays, and antiderivative of e to the power of t is exact same e to the power of t, just like the formula says. Now, here comes that substitution. When I try to take e to the power of 2t and integrate, last time I was guessing the answer, but here's the standard way to go. So 2t is not in the formula, but I will replace it with letter u. So I'm going to end up with e to the power of not x, but u. Okay, so now I take derivative. Same way I just tried to show you my unsuccessful trial. So I take derivative of 2t is 2 with respect to t, and derivative of function u is du over dt. Derivative of function u with respect to t, which means that 2 times dt is equal to du. So what is this for? Well, I'm going to be able to replace, look at this, 2t, I'm replacing with a new variable letter u. So my integral is going to be e to the power of u. And the other part, dt, which is here, without a 2, so I'll put 2 in denominator, so it cancels, will be du divided by 2. Notice that we don't put any operations in between. It means it's times, they're multiplied. And now I can utilize this formula again, but the variable will be letter u. So it'll be 1/2 u to the power of e to the power of u plus the constant. But there was no letter u. In the original exercise, I had 2t, so I'm going to go back, and instead of letter 2t, instead of letter u, I'm going to put back original variable t, so it'll be 2t. So this thing, I better put here on the first place in my answer. So it's 1/2 e to the power of 2t. And the constant is already present. Please notice, if you decide to take derivatives of this, you will get back to your original function. You can check this out. You can take derivative of 1/2, it's still going to be 1/2 e to the power of 2t, so it's going to be that piece. But 2t has derivative of 2. By the chain rule, 1/2 and 2 will cancel. That's why it stays. For the next one, the derivative will be same, 2 multiplied by e to the power of t. And for the last one, if I take derivative of t, it's going to bring me back to 1. So I say that's interesting. This is something very new. And that's why I would say next section is going to be a key section for us here that actually called integration using substitution. So I'm going to substitute for convenient letter. So I'm going to just do problems from the next section. My goal today is to do quite a few of them. And then, so that's section 5.2. So when you see this first time, I know it's just wondering and asking yourself, what is going on? I hope that maybe sometime tomorrow, you try to look at these again with a piece of paper and pencil and try to do them on your own. And then we'll do more of them on Wednesday. And after that, you should start to feel a little bit better. So let me start with exercise number 3, where we're going to have to take antiderivative. So that's section 5.2 of 2x plus 6 in the parentheses. And this is also raised to the power of 5 dx. Well, see, if you're going to get rid of power of 5, you need to multiply this parentheses 5 times with itself. It's going to be a big, messy expression. That's why nobody wants to do it. Whenever you see parentheses, advice is substitute it with a variable u. In this book, it works. Sometimes it doesn't. We just saw, based on the previous trial, where I had to actually distribute like that. But that was square, but now we have power of 5, so it's not really that convenient. So anyways, I take derivative of 2x, which is 2. And what people do, instead of to write du over dx, they put du here, and right away dx will go to the other side, so you don't have to mess every time with fraction, then bring to the left the dx. So that's standard step. So the point of this so-called substitution is to replace parentheses with something nice, with a new variable letter u. The reason you want to do this is because now you produced yourself a pretty straightforward expression analogous to the power rule for antiderivatives. But I also need to know what dx is. So to get dx, looks like there are 2 dx. So in order to pull out dx, I just go ahead and divide that du by 2. So that will be times du over 2. Just like that. And we have a good start for our antiderivative. So we're going to have to add 1 to the power. So we're going to have to put u to the power of 5 plus 1 divided by the same exact 5 plus 1 according to our formula. So the whole point is to take antiderivative. That 2 is still being denominator, so I can just have like 1/2 multiplied by this. And of course, plus the constant. So it looks like we're going to have 6 here on the bottom, right? So 2 times 6 will be 12. And instead of u to the power of 12, I always, sorry, it's u to the power of 6, right? I produced 12 because I had to double it because of 1/2. I have to always return back to my original variable, which was x here. So I have to put this, whatever, in the parentheses, 2x plus 6, just formally to write down the correct variable, because u we utilize to help us with that antiderivative. So here's my little answer. So the process is analogous to the previous substitution. And the whole point of this process is to be able to use the formula, because we don't have many formulas. One of them is e to the power of x, so I need to have e to some power, or the other is just a power of some kind of variable. And if that's parentheses, it's not the variable. We need to take this parentheses and to replace with a new variable. And that's the reason why whenever I see parentheses, then I just replace it with a new variable. So let's try problem number 9 here. That doesn't have parentheses. But technically, I could treat the power here as if it was in the parentheses. Look at exercise number 9. It has integral of, I'll put e to the power of x squared on the first place, and then multiplied by x dx on the second place for convenience. So we can better see what is going on. So technically, power x squared could be treated as if it was in the parentheses. So I'm going to do the substitution of this power with my favorite variable letter u. So this way I'm going to get this formula above at work e to the power of u. And now I need to also replace the rest of it. So take derivative of x squared, which is one of my favorites. It's 2x, right? And I attach dx to it and have du on the other side. So that's a standard step. So now I'm able to see that x squared we replace with letter u. And now I need to replace dx. Notice the 2 is on the way, so I'm gonna get rid of it, divide by 2 both sides, and this way I can see what dx over x dx is. This is actually du over 2, right? And this is my replacement. Because this over 2 really means nothing. It's just gonna have a 1/2 as a factor on the outside. So now I'm using this result, my favorite formula, e to the power of u will give us same exact e to the power of u plus the constant. And then I'm going to end up with the power x squared back. And that's it. So I hope eventually you will be grasping the key idea of this process, replacing in such a special way that we could apply our formulas. So no parentheses needed here. Say an exercise like number 15, we have denominator. Well, denominator plays the same role as if it was parentheses. So let me do number 15. So 2y to the power of 4 is on the top. I think for convenience, I will put 1 over y to the power of 5 plus 1. And then this numerator, I can multiply by dy. So that'd be my y squared. Actually, no, 2y to the 4th times dy. So my numerator, I can take off from that upper part on fraction, because indeed, when you multiply this 2y to the 4th times 1 will return me back to the original exercise 15. Because this way I can better show you how we substitute. So some differences, denominators, I put with this letter u on the bottom. So my new integral will look like 1 divided by, and instead of that sum, I just put letter u. And then we're going to times this by, now we better see what our substitution is telling us. So if y to the power of 5 plus 1 supposed to be replaced with a u, then its derivative, remember 5 goes on the ground and y will be raised to the power of 1 less with dy attached. is going to be du. So this is my other piece. So looks like we're going to replace that expression with du, but there is a 2 and here is 5. Well, first of all, I don't care for these constants. I can always bring them to denominator on the other side. In fact, what we're going to do with this 2, I can put it on the outside as a factor because it makes no difference, times 2, so 2 goes out. And then without the 2, y to the fourth dy, y to the fourth dy is exactly replaced with du over 5. So 2/5 will be on the outside, 2/5. And then 1 over u is going to be given me the logarithm, another formula. You see 1 over x is like 1 over u, so it'll be a logarithm of that variable and plus the constant. So I found the antiderivative. That's the whole point of this process. And then, of course, I need to go back with my original variable letter u. So 2/5 is going to be multiplied by ln of this u to the power of 5 plus 1 and the constant. So it turns out we're doing pretty much the same procedure. We substitute, we find its derivative. We substitute, we find its derivative. So that's really same thing for all of them. Let me do one more. Right? I hope you're not getting tired of these manipulations because they are indeed something different. May seem to be pretty straightforward when I do it because I practiced a lot. I practiced all night and I was just practicing again. And the more you practice, the better you get at that. So I'd like to take problem 23 that again has logarithm, but the logarithm is not in the position where we need it. So we're going to integrate ln of 5x divided by x. So again, I want to separate. So I'm going to put like 1 over x dx. So this way, usually we can better see how substitution goes. So there's denominators we try to separate because there is no formula that enables me to integrate ln of 5x. So it turns out whenever you have natural logarithm, you always want to replace it. So ln of 5x, I'm going to replace with a variable letter u. And then I take its derivative. Remember what derivative of ln x? It's 1 over x. In fact, you could check it here. Derivative of that is 1 over x. So what's the derivative of ln 5x? Well, it's going to be 1 over 5x, but chain rule says, Alex, you have to also multiply this by derivative of this 5x, right? Which is 5. And of course, you're going to attach dx to it and have it equal to du. So this way I've got this, I guess, du pulled out, 5 canceled, and look at what we have here. 1 over x dx is exactly what we have here. So this could be replaced with a du, right? And what about ln of 5x? Well, we decided to call it as a letter u. So it'll be integral of u times du, just like that. So it is nice looking antiderivative. Power rule is what I have to use. Remember, u to the power of used to be 1. Now I add another one, it's 2 divided by 2 plus the constant. And of course, instead of letter u, I put that ln, which is squared and plus the constant. So doing these exercises, doing them more and more and more, I hope makes you feel more and more comfortable. Now I want to say a couple of words about this constant as promised, because turns out it's not just one constant, it's a family. Family? Yeah, I think they should have a nice picture here, because if I start drawing picture, it's not gonna be that nice, because in the book they have beautiful pictures. I was always jealous of their pictures, but it turns out that it's hard to make those. So if I could use theirs, it'd be nice. Let me see. Here it is. The story of constant. So let me get a little bit of room. So maybe I can clean this a little bit. So it turns out that they found the antiderivative for some kind of function, which is 3x squared. Calculate this for you. So if they try to find the antiderivative of whatever, 3x squared, dx, of course. So dx and integral sign always here with us. So that's what they're actually talking about, 3x squared function. So 3 stays. According to the formula above, power of x will be increased by 1, so that'd be x to the third power, 2 plus 1, and divided by 3 plus the constant. So I actually have x cubed plus the constant. So what does this mean? It means that the constant could be 0. So that's the red graph, x cubed, right? If constant is 0. But the constant does not have to be 0. For example, constant could be 1. So that'd be this graph, moved 1 unit upwards. Or constant could be, as they say, -5. So that'd be the graph of x cubed moved down 5 units. The point of story, depending on constant, your cubic function, cubic parabola, either will be moved up or down, depending if constant is positive or negative. How about that? In fact, they say at any point that you can imagine on the xy plane, you can find the function that passes through it by actually finding that particular value of constant. So it's not just one function for the answer. There are infinitely many of them. So it's really a lot of things. And if you're just losing this constant, it means you're losing infinitely many solutions. You just end up with only one, which is definitely very incorrect. And that's why it's very important to always remember not to lose that constant. Maybe next time I'll find a problem where we're gonna find antiderivative and then do one more step to find the constant. But first, I want you to really practice on this section 5.2. As I said, it's a key section for this rest of the class time, because we'll keep on dealing with finding antiderivatives and we'll use substitutions. So that'd be something to get used to. In fact, this chapter as well as the next chapter just keeps on finding those antiderivatives. And I don't think I'm going to give you a quiz on this because it's substitution. It's a little bit different. But I'd like you to try to look at the problems I did today. Well, as usual, a couple of problems should be good enough for homework. If you want to practice more, of course, it's just better for you, for your understanding. Because next time I'll go over this again, because I know it deserves extra time. And well, we have it. That's the good thing. So we're in a good shape covering this story. And if anyone wants me to do some word problems, please let me know which ones, because I try not to select many of them, but we can always do something. Just tell me. And usually it's really something with tedious numbers. So I think eventually I will select one. I think just for today is plenty of information for you to comprehend. So I'll just let you go without a quiz. And on Wednesday, we're going to continue. So I'm going to stop this recording and let you enjoy the rest of the day.